Hi, we are group 3 from 6A, 6A. My name is Ainun Nabil bin Kamarul Azni.
Hi, my name is Nuri Shahida.
Hi, my name is Nur Amira Atika.
Hi, my name is Nur Aisha Alawiyah, and today we are going to do a road safety audit for our mini project.
This is the main road that we choose within the UiTM Shah Alam, located in front of Melati College. This location was strategically chosen due to its prominent vertical curved road. Our first major safety issue identifies a dangerous combination of vehicle speeding because this segment features a prominent vertical curve. Drivers naturally accumulated downhill momentum and this becomes incredibly hazardous due to restricted stopping sight distance at the crest. The second critical concern is the high traffic volume during peak hours. As a primary spine road within the UiTM Shah Alam campus, this road experiences heavy vehicular load during class transition. This high density creates a chaotic flow mechanism where vehicles continuously stream over the crest, leaving no safe gaps or dedicated intervals for other road users. This brings us to our third and most pressing issue, pedestrian vehicle conflicts. This road serves as a main pedestrian corridor for students. When the high traffic volume overlaps with thousands of students walking to class, a massive conflict zone is created when vulnerable road users must cross paths with fast-moving oncoming vehicles that have limited visibility. First, speeding. Exceed the speed limit. Drivers frequently exceed the speed limit within the campus, increasing the risk of road traffic accident. Second is geometry layout, vertical curve. Next, obvious features which is vertical curve. As you can see, the hilly terrain naturally restricts the stopping sight distance for oncoming drivers.
Third, cross-section, lane width and sidewalk. Zooming into the road, the cross-section layout and step alignment can affect bicycle operation. It also has sidewalk for student daily use. Vulnerable road user infrastructure. Pedestrian crossing. While there is a pedestrian signage present, our audit evaluates whether these visual aids are strategically placed or insufficient to warn fast-moving vehicles about vulnerable road user crossing the crest. Fifth, roadside safety features. No guardrails. The absence of guardrails increases the risk of severe crashes, particularly if a vehicle leaves the roadway. Street lighting for clear view during night. We observe the street lighting dedicated to the pedestrian walkway, ensuring adequate illumination at night is vital, as poor visibility combined with a highly geometry increases the nighttime crash risk. 7. Visual aid, convex mirror. Lastly, a convex mirror has been installed as a visual aid to improve sight, distance and reduce blind spot at the horizontal curve. To justify this safety hazard, our group will implement two crucial traffic engineering methods, which are
As spot speed study analysis. We need to collect actual speed data to calculate the 50 percentile speed, the speed at which most drivers travel. If this speed is higher than the campus speed limit, we have scientific proof that the geometric design of the hill encourages enforced speeding. Second, traffic volume analysis. By counting the number of vehicles and pedestrians during peak hours, we can determine the conflict points and the level of exposure. This justifies why the pedestrian signage and street lighting shown in the video are crucial. If the volume of students crossing is high, then any lack of visibility or poor lighting multiplies the risk of several accidents.
But before we even touch any equipment, safety comes first. Wherever you are working in live traffic, always gear up in a high visibility safety vest, so driver around you can see you clearly. First up, for our spot speed study, we have the measuring wheel. We use this to quickly and accurately mark out our track distance along the pavement. Next, the laser speed gun. This device lets us capture the instantaneous speed of individual vehicle passing through our study zone with pinpoint accuracy. Just aim, click and record. Now, shifting gear to our traffic volume study, to keep track of the number of vehicles passing by systematically, we use this multi-unit manual tally counter. Each clicker button is designed for a specific vehicle classification, like motorcycle, car or bus, so we can count them simultaneously without messing up our data. We start by resisting our measuring wheel right at the starting line to measure our track distance for the speed study is precise. Then, we walk out the road till we reach our required distance and mark out the final distance 60 meters. First, let's look at what not to do. Standing right at the edge of the curb is a major safety hazard that leaves you completely exposed to passing traffic. Instead, here is the proper precaution step. Always stand well back from the roads. Using natural barrier like tree for extra protection, this keeps you safe while preventing driver from braking when they spot you. Now, for the tracking technique, when you use the radar gun, you must smoothly target and follow the moving car until the gun locks in and display the final reading. Keeping your aim steady as it moves ensure maximum accuracy. Here is exactly how the reading displayed on the radar gun. Once you target the vehicles, the screen instantly locks in the data. The left value tells you the precise speed on the oncoming vehicles, while the right value indicates the exact range or distance from where you are standing. Switching gear to traffic volume study, to keep track of the number of vehicles passing by, we use this manual telecounter. We can easily classify and count different types of vehicles simultaneously like car, motorcycle, and bus without losing track. Then set timer for 5 minutes and start to observe. While one person focuses entirely on filtering and classifying the oncoming traffic, the other track our time interval on a smartphone. This ensures our volume data is perfectly organized into specific time slot.
Once your specific time interval is up, always log your final clicker totals onto your field data sheet immediately before resetting the dials back to 0 for the next round. To get a complete count for both directions, our team decided to split up. My groupmates are stationed across the street to observe traffic moving to the right, while another stay on this side to monitor the traffic heading to the left. By capturing both left and right directional flow simultaneously, we can accurately analyze the road's overall capacity and peak flow density. For the spot speed study of 100 vehicles, our calculation shows a mean speed of 29.05 km per hour and a modal speed of 27.0 km per hour, where the highest density speed class of 25 to 29 km per hour captured 47% of the total traffic. With a tight standard deviation of 4.85 km per hour, this numerical data indicates that vehicle operating speeds are highly clustered together near the 30 km per hour threshold as they approach the hill. Plotting this data visually, our frequency distribution histogram shows a sharp bell curve peaking right at 27 km per hour. Meanwhile, our cumulative frequency curve at the 15th percentile confirms a median speed of 28.3 km per hour. Geometrically, both graphs prove traffic consistently travel near 30 km per hour over the crest, critically restricting stopping sight distance on this blind hill. Next, our 60-minute traffic volume study matrix during peak hours reveals heavy vehicle density, with Direction 2 experiencing significantly higher demand than Direction 1. According to our pie chart, the composition is heavily dominated by motorcycles at 25% and passenger cars at 24%, meaning small commuter vehicles make up nearly 50% of the entire value. Synthesizing these datasets confirms that high traffic volume combined with a 30 km per hour operating speed multiplies both conflict probability and crash severity on this curve.
Our group proposed 4 targeted engineering mitigation to systematically manage vehicle speeds and protect vulnerable road users along this high-risk vertical curve. First, we proposed the installation of speed humps or raised tabletop platforms directly before the pedestrian crossing. This physically forces oncoming drivers to reduce their speed to a safe threshold, mitigating the downhill momentum right within the high-risk pedestrian conflict zone. Second, to solve the visibility limitations, we recommend the implementation of solar road starts and raised reflective markers along the approach lanes. This significantly enhances the driver's visual alertness and hazard perception, particularly during nighttime operations and heavy rain when vertical curves become hardest to navigate safely. Our third measure is the deployment of standardized speed limit and warning signage. Installing clear, highly visible pedestrian zone warning signs alongside a street campus speed limit sign of 20 km per hour provides advancing drivers with sufficient reaction time and explicit visual cues to begin decelerating safely before reaching the crest. Lastly, to manage our massive peak hour congestion, we propose upgrading the existing uncontrolled zebra crossing into a pelican crossing, which is a push-button activated pedestrian light system. By regulating traffic interruptions, this system forces pedestrians to cross in coordinated, visible groups or batches. This directly minimizes erratic stop-and-go vehicles delay during peak traffic hours and balancing both operational flow, also pedestrian safety.
By combining this physical traffic calming, active visual and regulatory measures, we can successfully eliminate the critical conflict points at this vertical curve section. That concludes our presentation. Thank you very much.